Okay, let's go ahead and start. It is my pleasure to introduce Dr. Christopher Kanan, who is not only a good friend, but a longtime collaborator and is currently an associate professor of computer science at the University of Rochester and has several secondary appointments with the Kanan Institute of Data Science, Center for Visual Science, and Brain and Cognitive Sciences. He's been a great partner when we tried to launch the AI Center at Rochester Institute of Technology. Since then, his research has been focused on deep learning, particularly using continual machine learning, where he works to make neural networks capable of learning over time for large-scale vision and multimodal perception tasks. He has created multiple state-of-the-art continual learning algorithms that are popularly used in the community, lots of analysis on benchmarking and also metrics for evaluating these kinds of models. He also has worked on open world learning and creating biased, robust neural network architectures. And he also has been working very actively on several applied projects using deep learning, whether they are including those in pathology, radiology, and nuclear fusion. And his work, I think, in pathology and radiology, perhaps is one of the first in the nation and has got a lot of recognition through a startup venture he has participated in. And perhaps he's going to briefly mention that. He has also received a NSF Career Award, and I think the list goes on, but I think he has done tremendous work in deep continual learning that has been actively used in the community and well respected in the machine learning research group. So I'm honored to have him here and speak more about his research. Thank you, Chris.
Thank you so much, Judy. So thank you for the invitation, and let's get started here. So some of the stuff I didn't know where my audience would be, but deep learning kind of brought a lot of AI together. Like we used to all be really separate, all had separate tools, and now everybody has kind of like this common toolkit, which is very useful. It means we can talk to each other more freely. Different problems, but at least we got the common toolkit. You don't know deep learning. I'm guessing all of you do. Rebranded neural networks. They have parameters that we fit from data to learn something. They can have a lot of parameters, like 300 billion plus. So a lot of parameters, and they learn from data to fit these parameters. Being used across tons of industries for all sorts of things, ranging from face detection to special effects to writing spam on the internet to editing documents to banking and finance, protein folding, physics problems. I'm using it for inverse physics problems and nuclear fusion, something I never knew I would do. A physicist came to me and said, "Hey, I have this problem. Can deep learning do it?" And I'm like, "Well, I can write a proposal for how it might do it." Pathologies. This is where I worked on this for about 3 years, and I'm still working as a scientific advisory board for that company. We recently released a foundation model, named it after the founder of pathology, Urkov. So a very bold, this model's got, over a couple billion parameters, and it's trained on more data than Netflix has in videos. You gotta it's a startup, right? You gotta talk to the media. So, but yeah, I'm very proud of that, and also a lot of other collaborations. You got autonomous cars and robotics, just tons of stuff. I mean, I'm excited about this application, automatic dubbing. Hugely disruptive. A lot of people are very worried about, especially now with ChatGPT for jobs, artists, and all these things. But I think they'll bring a lot of benefit to society as well. There's a lot going on, but there's also some cons. One of those cons is this environmental impact. So even though it's affecting just about every field, including education. I was at a meeting yesterday where people from Ohio State said every degree at the university now has the option to be plus AI. But there are even like things that you might not expect, women's studies plus AI, like you can do that now here. So, however, there's an environmental concern that people are raising. So here's an article: AI can do great things because of the planet. And if you kind of look at this, we're kind of on this. Unfortunately, Moore's law died out, but that doesn't mean we aren't still trying to exponentially use more compute. So people are just throwing more machines at it, and this is increasing. This is on a logarithmic axis. So this is like you're using orders of magnitude more to build up in this plot, and this is where we are with very large foundation models I just mentioned, like GPT-4. I mean, we don't really know how much it because OpenAI no longer talks. It provides such information, but a lot. And if you were then, there's a study by UMass Amherst looking at the average amount of carbon released through training a GPT-3, and that's that little robot there. So it's about the same amount you as an American, if you weren't American, you would produce less carbon, but you in your American lifestyle would produce over about 17 years of your life. And maybe you would say that's okay, right? Like, hey, look how many people use this thing. It's very useful. However, they do need to retrain it. So that's one run. It's one time it learned 17 years of the amount of carbon you release. So, these things are expensive. One thing people may not also think about is, people are very worried about water in many parts of the country and the world. GPT-3 used about 700,000, is estimated to use that training run, 700,000 liters of fresh water for cooling that's then evaporated. So use a lot of water too. They're not using salt water, they're using fresh water. So, there's some costs. And one of the reasons why we need to retrain these models is to give them new knowledge, because the way we do it nowadays is you learn once and deploy once. If you want to teach the thing new tricks, well, start over, do it again. So that's hopefully we can do better than that. So that's kind of like where my work comes in, and this is one of the major applications people are interested in for. So let's talk about continual learning. So basically what we're trying to do in continual learning is overcome this paradigm where we have a training set and a test set that's supposed to be representative of the real world, and then we train on the training set, and then it is deployed, and it does not learn again. In continual learning, our goal is to keep learning. So we don't just learn once, we continually learn. Like we do as humans or other animals, right? We aren't frozen in time. So that's continual learning there, right? The data, deploy continually, versus learn once, deploy once. Now, of course, if you're going to change your architecture, this can't help you there, right? So if you're going to change your whole neural network architecture, as long as you retain the same architecture, how do you update the model? And a lot of companies are asking for this when I talk to them about it. This wasn't my original motivation, though. I mean, my motivation initially was just scientific curiosity. When I was a graduate student, it was pre-deep learning being hot, and so there was very little out there. So I read a lot of old papers, and I read this one paper as a graduate student about catastrophic forgetting. It was a review by a person named French that referred to this earlier work by Mike McCloskey and Neil Cohen, who were psychologists, and pointing out, talking about the problem of learning. And then I had a very productive PhD student who did PhD in just 3 years. And after about a year and a half, he said, I've written 4 papers now on my PhD topic. I'm bored. Can I do something else? I'm like, well, there's still learning thing if I want to work on as a graduate student. So then he published 3 papers on that. He had a master's degree. He was in the Air Force and just worked like in the lab at 7, gone at like 7, and he worked weekends. This guy was a machine. Anyways, he recently won one of the highest award the Air Force can give in science and engineering. Anyway, so AGI. So I was interested in like most of the problems. Whatever I say is a major thing in trust in my lab is usually me thinking about trying to do artificial intelligence, but just thinking, well, we can't do that very well with today's AIs. We can do that, and AGI should need to do that. So that might be a good problem to work on, right? How do we kind of like overcome the limits of today's technology by saying, okay, we can't do that, we can do that. Or deep learning can't do that, we can do that. So let's a good problem where we learn continually. So here's Mike McCloskey and Neil Cohen. So they found when neural networks were known as parallel distributed processing, it keeps being named different things. They found that just updating network on new data doesn't work with conventional methods because you end up with catastrophic forgetting of previously acquired knowledge if there's distribution shift. So you have to have the distribution change. The network forgets what it used to know and only learns new information. And the greater the distribution shift, the greater the catastrophic forgetting. One of our earliest papers, usually when I enter into a space, I'm like, let's just compare the handful of methods out there. And there were almost none. There was like 4 or 5 methods. There was like 5 methods or something. Nowadays, this would don't stand. If I just wrote them out in like 10-point font, probably be all the way to the end of the window or more. They always compared them. So always when I start a new area, just like see how good this current data are. Compare things fairly because usually everybody's setting things up differently. And what we found in that paper was class incremental learning was very hard, and that everything started to fail. So learn apples, when we have class incremental learning, we mean learn apples, learn pears, learn grapefruit, etc. So this was a very adversarial distribution. Unfortunately, this work then led to the community doing things that I think are very self-harmful. Why did I do this? I did this as I was trying to figure out what's a good distribution to target to study this problem. People started developing algorithms for the important problem of class incremental learning. This is a weird test distribution. It wasn't as I thought of. I didn't think it would become something people would build custom algorithms for. Nobody needs this. It is a test. And the community has been focusing a lot on this catastrophic forgetting problem over the past few years, and now it's largely solved. And I think we need to move on and think about other considerations. So it's largely solved with some assumptions. So if you don't make those assumptions, you can still, and we keep taking away more and more assumptions to make it harder and harder for ourselves. But those assumptions will keep restricting you or may not be rooted in any reality, any real world application. So I'm going to argue that without considering aspects beyond catastrophic forgetting, like why are you doing this, that your work may be pointless. The real world impact, we need to develop algorithms that match real world needs. I'm not saying everything we should do needs to have real world impact, but it's really should be not aligned with a scientific hypothesis. Machine learning, everybody's just concerned with, hey, I want my numbers to be a little better than that other paper's numbers. How do I achieve that? And that's not being good science. And they're not thinking about even like, why am I making this? Why am I doing this thing? It's just trying to publish. I'll give you two examples of your audience is other people doing the same thing as you. And that's not what I think necessarily healthy. But anyways, but 2 use cases where I have been approached by many people in industry where they have a desire are these 2. So I'm not saying these are the only applications. These are 2 applications. Updating production AI systems with on-device learning. So I already alluded to this, but in industry, especially in places that are like, they're using AI, but they're not like iterating on the AI all the time. They built it up. They know what they need to do. Their data sets are growing continuously. What they'll do is they'll have a job that will trigger periodically once the data set grew a certain size, or whether, maybe on a monthly basis, something like that, where they'll retrain the whole network and then redeploy it. And what they really want to do whenever they read about machine learning is they hope, wait, that would probably help us do this more efficiently so we don't have to do this thing like this. And they find that machine learning algorithms are woefully inadequate for them because they're not willing to sacrifice any performance. So any gap is too big. It's no gap. And it needs to provide some benefit. What benefit would we want to provide? Speed. should be faster, right? And if we're faster, we're using less power and apparently saving water too, and releasing less carbon. So good. On-device continual learning, and no company I'm aware of is actually doing this because everybody I talk to says is what we want, and nobody will give it to us. On-device continual learning is another application. This one I know, so several AR companies have reached out to me about this. They don't publish any papers, I don't know what they're doing. So some of the AR community really, the AR companies, guess which ones they are, they don't seem to publish any papers about this, how they're using healing, but they tried to talk to me about recruiting me for these applications because they're using them on these devices to set up stuff, right? You can think of, we're very nervous for these are just me speculating why they're nervous about doing it in the cloud, both due to latency problems and even more concern is probably liability, right? Because as soon as you are wearing a device around the house, you might see somebody naked and it needs cameras and they don't want to be uploading that data to the cloud and get themselves in trouble, right? I mean, Amazon got themselves in trouble with this. They had their iRobots driving around and taking photos and sending them back and people in the bathrooms. So that's not so good. That's so good. Send it back for annotators. So what would we need for this? So in the previous application, companies don't care about storage. Like storage is pretty cheap right now, so they're not really interested in that. But for this, you have a very constrained storage. You have a very constrained amount of compute. People will even talk about, if you want to be really useful for on-device learning, we're going to use an ensemble of 10 vision transformers. You can't do that. The very big, reasonably big neural networks. You can't do this on your phone. This isn't going to really work. So yeah, the other here you'd also probably need some ability to learn from very few examples because your human user is probably not going to be willing to provide 100 annotations for you for a given task. So trying to make this table here of what people care about. So something like must match offline model accuracy. So production AI, they're like, yeah, we don't want to burn the planet. We lost 1% performance. Retrain the model. Must save money. Must save money. They don't care about that. Storage constraint, production, they don't care. On device, you have to deal with that. Sample efficiency, that I'm checking there because they want to see it getting more efficient over time. So it's kind of redundant. But yeah, we're going to need some sample efficiency. The ability to do low shot learning, definitely on the on-device, effective for arbitrary learning distributions. Both of them need that. Nobody needs classic mental learning. Tests, you don't know what distribution you're going to get. Maybe it does have new classes, but you think it's going to have only classes in order? And if you take somebody's code, you download one of those papers, it won't run. Like if you give it things where the classes are revisited at all, it won't run. like they made them so rigid. A mobile architecture, yes, on the on-device. Pre-trained network, this is very controversial in the community. But this is what everybody does, like in industry. They all start with pre-trained models. And the machine learning people, the machine learning research community kind of decided for no reason that's not machine learning. But that's what people are asking for, what they need it for. And now everybody's moving towards pre-training the foundation model and kind of doing it, capable many tasks. Literally what people are doing, right? Across many disciplines. So why don't we do it with machine learning? So yeah.
I didn't see latency in there in your chart. Is that?
We could add that too.
I think that's very important, right? For on device, yeah.
It is. Even the production AI. So because if you have reduced latency, you're probably reducing compute. If you mean just a pass through the network from your input to the output. So ChatGPT is estimated to cost $700,000 a day to run, and it's very hard to. OpenAI just started a project that couldn't get it to work, named after like the planet Dune, where they're trying to make it fast, like reduce the latency. But the main reason they care about the latency though is price. $700,000 a day, a lot of money. So skill learning, and this is some of these slides are kind of aimed at the skill learning community, but a lot of these papers, you read the papers about these two, are guilty of Goodhart's law. So when a measure becomes target, it's become a good measure. But then it's just like the classic kind of learning. Like people just kind of like so kind of lost sight of what are the criteria we need for healing to be useful versus I beat that last paper. So without rethinking, hey, does this make any sense? Like I sometimes even if you like are one of the founders, I don't want to say a founder of this niche, right? People were doing it in the '80s, but reawakening it. I didn't think everybody would start doing this and making algorithms exclusively for this task. And it's not just me, but we were some of the, well, that was one of the main results of this paper, and other people hadn't shown that yet. So yeah, is it useful? Yeah, it's useful as a test, but is that what your algorithm should do? The other thing is, at least in my community, I have my iClear papers for review right now. I don't know why I agree to do this. Almost all of them are like, we use MNIST and C10. And I don't understand why, because they're like, we use tons of powerful GPUs. They're not trying to do something like some bespoke neuromorphic hardware. They are using a bunch of GPUs and big neural networks on toy data sets. And those papers will be accepted because that's what the community is doing. And I don't know why it hasn't grown up. One of the issues people say is it costs too much. It costs $10 to train ImageNet. I'm not saying ImageNet should be our gold standard, but it's way better than this because most of these algorithms don't scale up, right? You pick 10 possible ways to do your incremental class learning or whatever you did, right? You set it up. Not that many. Your findings here may not generalize, and every time I replicate one of these models, like 9 times out of 10, they don't generalize. They work only on the small scale. So I don't think it's an excuse to say. And one other issue is a lot of the algorithms I'll show you may use a lot of storage. And I'll also do studies with less storage. But people complain saying, too much storage, so you make the prompt too easy. I'm like, well, there's still a very hard gap you have to close, the warm start gap. Um, but um, um, but the storage is about 66 cents as of 20, I think 18, so it's probably come down more. I couldn't find a number, but industry doesn't care. They care about compute. Remember, $700,000 a day. We got to reduce that. So I'm both good with if you. I mean, storage constraint does matter. Like on device, you got to deal with your storage constraints. Great. Then your whole paper should be all your choices should be aimed at things like that, rather than all your choices being arbitrary. Um, um, okay, so I told you we maybe Q-Learn could offer a pathway forward for this efficiency stuff. Unfortunately, we put out a paper just tracking how efficient are they. So here's the offline model that's trained from scratch. Here's our continual learners. It's more expensive. Why do this? It's worse. Um, um, you just take their papers, you read what they did, and you figure out how much compute did they use and map it, and then make this plot. These are all slower. This one's not as like this line, but from several years ago. We didn't even realize it was faster. We just made this plot this year. So I'm like, I gotta somehow start making stuff that's easy and catchy. So I'm going to tell you about 3 projects from about the past year and a half to try to address this. So we're going to use ImageNet mostly. So first one, so bunch of it. First one's Siesta. It was accepted today to a journal. I kept trying to get it accepted to top tier AI conferences and keeping reviewed by Q-Learn people, and they hate it because it doesn't align with the assumptions that are kind of like I helped establish. Did not know it would become dogma. So, yeah, I've been giving talks like this for 3 years. So anyway, Siesta. Um, it's heavily inspired by an earlier algorithm from my group with a few modifications. That's one of the bigger complaints they have. And I think that might be okay as a complaint, but it performs way better. But it's based on some findings from neuroscience or some hypotheses from neuroscience, I would say, where we kind of are caching compressed representations of temporally correlated experiences in our hippocampus. We're going to kind of like not worry about the temporal correlation. But priority is given to salient or novel information in this kind of buffer. And if you don't have this buffer, the hippocampus in the brain, you kind of can't learn to semantic information. We'll have no players. During sleep, these representations are kind of consolidated and transferred over for long-term storage to other areas of your brain. So siesta is based on kind of two general ideas here. One is a theory known as hippocampal indexing theory, that the hippocampus index to reactivate cortical areas for the replay. And the other one is use compressed representation, in that the hippocampus is located kind of midway point in your brain, I would say. Like, you don't have a lot of projections from early sensory areas, from early sensory areas to the hippocampus. At least not after development. I don't know if there are before development, or before development stage. But anyway, so a lot of methods that use a method called rehearsal, which is basically consists of mixing old and new data together in order to stop, mitigate this catch-up forgetting thing, right? Basically make the distribution less look like a new distribution, like mixing in old stuff. A lot of these algorithms will just store raw inputs, and our argument is, well, that's biologically plausible and not really the right way to do this. So instead, we have some frozen layers here. So these layers are learned during a developmental stage and then frozen, and then we kind of buffer them in our kind of Campbell-like mechanism in a compressed way such that they can reactivate. And we do it with a form of tensor compression such that it takes up not that much memory. And then basically we can reconstruct them and train all the rest of the network during what we call a sleep phase. So this algorithm alternates between a wake and sleep phase. That's what differs significantly. There's a bunch of like little things, but this is the biggest change between our earlier work called Remind and the siesta algorithm. Is like Remind basically used this rehearsal mechanism where it would get a new input and then it would sample 50 old inputs, mix it together, and update the network. Instead, this one just, but that gives it no ability to really choose what should I update next based on my experiences today. And so instead, basically, it learns during its daytime in kind of like a weak way, and then when it goes to sleep, it learns in a more intense manner. So this is kind of how it works. So we have this frozen area, storage, and then, and during its wake phase, these things are frozen, but its output layer is updated. And then during its sleep phase, we can sample the storage in order to update the rest of the network. There's a lot of tricks in here. The first trick is we have a developmental stage, we call it phase initialization, where it learns kind of universal features with self-supervised learning. But it learns it on the same amount of data that the existing machine learning papers do, like as their first batch, which is not small. It's like 100,000 images. So like, here's 100,000 images, here's the next 100,000 images. These are 100,000 images from 100 classes on ImageNet. So we do this using a self-supervised learning algorithm called SWAP. There's a bunch of details, but essentially it compresses a 14 by 14 by 80 tensor into a small number of integers. And by default, it uses 2 gigabytes of memory, which is consistent that, I don't know how the community settled on 2 gigabytes, but that's what they decided was threshold. We are forced to kind of like align things to what the community did previously. Even when we're trying to break assumptions, if we break too many, people will really freak out. Only 2% of the network parameters are actually frozen, so 98% of them last. Yeah, so basically it sees n samples and goes to sleep and is allowed m backprop updates. So it's allowed only m. It's budgeted. It has a budget of m. Only skips so long, right? Because like it's 7 hours. It sounds like 7 hours, but m. And then we compute the total number of updates. So I'll skip this line. How do we do the online updates during the wake phase? It's just a little linear update on the output layer that we do to track like the class modes for new data. The sleep stage, it reconstructs things. It uses a balanced uniform sampling. We're going to come to this later as a better approach. It sounds like it's going to sound better than kind of class balanced uniform sampling for your buffer. Everybody's tried to find better things, struggled to find it. Quite a lot of effort. Found something, I'll tell you about it. But uh, yeah, so it researched 1.28 million samples. Sounds like a lot, way less than what others do. Sleep enhances learning. So you can see that we see a boost. Here's pre-sleep, you go to sleep, you don't consistently, so that's good. And we get this gets very strong results compared to earlier models. Like I said, kind of got a lot of similarities, a lot of differences too, but the differences are not like super vast between the two, but it's working like much better and trains 4.3 times faster. So that's great. It achieves zero forgetting. That's good too. So there's no catastrophic forgetting. There is an important caveat here. We are trying to be really good scientists. And if you read these papers, everybody's like comparing things, trying to be, I don't want to say really good scientists, trying to be better scientists, be better than others in terms of keeping like not changing like 50 variables and saying the only thing that matters is my novel idea. Well, you changed 50 other things too. So I don't know what was actually considered. For this work, all the models have augmentation turned on. So it's all initialized from the same way. Everything is kept extremely fair in this plot. In this plot, we see this zero forgetting happening. However, if we start using augmentations, we are still achieve better performance than everybody, but the star goes up. So we still are trying to figure out how to deal with that. But when we did hypothesis testing for never seen machine learning papers and found no significant difference between online Siesta trained with an IID distribution, very easy distribution, and Siesta trained with a classic Camaro distribution, very adversarial. So that's what we were going for there.
Just a quick question.
Yeah, go ahead.
How much M and N are important for this algorithm, and do they need to be kind of like consistent?
Good question. So M saturates, so you get diminishing returns after a certain point with greater M. We have a bunch of tables in our paper. I don't remember exactly when that happens. With N, it's hard to say. So it varied across these different data sets. And I don't think like get an N of one, you're see one thing, go to sleep, see one thing, go to sleep. It doesn't really, we definitely wouldn't get much of a benefit of efficiency. So I don't think we really measured N in some methodical way in this work. I don't think. There's so many experiments, so many, like some of the material is very, very long. I try to placate reviewers. If I say I gave up and spent to a journal that does not review policy, for the important scientific results. And they liked it. They're like, these are amazing results. This is the best model we've seen. Anyway, it requires 7 to 60 times fewer updates than other models. You see, like, here's that gap I was telling you about, right? Here's the augmentation model. But it's still working way better than all the other ones. The size of the circle represents the number of parameters, and it represents the number of updates. Over here, like this was a state-of-the-art model here, but it's picking. And everybody just usually doesn't measure any of these things. Nobody's measuring the memory, nobody's measuring the compute, nobody's measuring these things. They're just like, my number higher than your number. Well, fine, my number is higher than yours. So there you go. But I did measure all those other things. Okay, so next thing I want to talk about is graphs. So I mentioned earlier, which is in review, one person, Killer and Comey, most amazing paper he read in space. I don't know, but it was rejected. That's in review again. So they didn't like an assumption I made. So to study this assumption, we started with unlimited memory. So like in our, nobody reads supplemental materials. So in our main text, we said we're going to put in our results with unlimited memory. Because what we're how I talk about is how do you sample the buffer? The question is, how do you sample it? That was our scientific question. And so we said, okay, well, to do that, if we somehow need to prune our buffer, we're now kind of like asking multiple questions. I want to ask one question. Right? So anyways, and a lot of people, like I mentioned earlier, found this class balance uniform sampling is a very strong baseline. Like how I had a whole student working on this tip for a year, found nothing better. And I was at DeepMind earlier this year, talking about this, like, we don't know anything better. We tried, and it's a very strong baseline. And you can see, like, some methods perform way worse, but it's like most methods perform either slightly worse, but not better. So that's a problem. So we came up with this GRASP idea, which is based on this paper about, do you know what neural scaling laws are? It's about breaking neural scaling laws. It was a Harris paper last year. And I saw that, and I asked him, I think it's at the application skill learning. He's like, I don't know anything about skill learning. Okay. So I have an idea. But anyways, what they found in that paper was when you have they were studying something called data set compression. And they found that, if you have very little data, the best things to study were the easy samples. And if you had a lot of data, the best things to study were and you're only going to retain a small portion of the data set, the best thing to retain, or learn on, would be the hardest sample. So if you have a little bit of data, easy, a lot of data, hard. And if you're learning, our amount of data is changing, all right? So we go from a little to a lot. So we start with sample stuff near the class prototype, right? We can measure that in terms of embedding space, easy. Okay, and then as learning progresses, sample further away. As learning progresses, sample even further away, the hardest samples. That's the idea, uniform sampling, you're sampling uniform for class. The idea is pretty simple, and we end up with saving 9.2 million updates. So this is, and this is you storing just raw images. Like, we're just trying to keep everything constant in this plot. Again, it's like, let's do what everybody does, store the raw images, sample, and worry about no memory. We're just going to ask, can we build a better sample? That's just a question, plug it into whatever, once we try that. Let's see if can we do this. And here, to achieve the same performance as this uniform class balance, our method saves you about 9.2 million samples and achieve the same performance or updates rather, and it's a little bit better. Yeah, so that's and here's some minutes. Like, just updates if you look deceptive. What if your sample is extremely expensive to run? So here's minutes, still 1.6x speed up. And we then did memory constraint experiments as well. A supplemental that has been moved into the main text to retry number 2. People won't read your supplemental, be very careful. You'll get your rebuttal, you'll get your reviews, and you're like, I have everything you're asking for. It's in that supplemental. I even called it out in the text. But yeah, so basically we found our policy works very well here. Even if we constrain the amount of samples in the buffer, where we just basically, as the buffer would just drop the samples from the class with the most stuff randomly to constrain it. And then as we vary the amount of compute varying M, we see that this still works better than all the other policies. And then we plugged in the siesta, and then using latent rehearsal, and it compared that versus using the raw images, and it still performed, well, in both cases, GRASP performed better. The raw images did perform better than the latent rehearsal in this case. So, last one I want to tell you about. How much time do I have? I'm running out of time. Oh, great, I got plenty of time. Okay, last one. This was the paper. Sorry, I was confused. This is the paper that the first one was this overcome the stability gap in skill learning. This one was also got rejected, and the reason why, one of the reviewers said, I fundamentally don't believe that skill learning should be about studying networks that have already been pre-trained at all. And so and that was this comment. You didn't like it, we call it skill learning. But anyway, so there's this phenomenon. I suspect, but it's gonna be on YouTube. Oh no. Anyway, so you're getting my translation here. So here's the task 1 accuracy. And normally when people don't learn, they measure performance after learning the task, right? You learn your task, you do something to mitigate catch-up forgetting. The next task comes. Between each task, you measure performance. In this paper, what they did was they measured performance continuously. Like every time you get a sample, you measure what happened. And then what you find is every method seems to mitigate the catastrophic getting, but as soon as you get this distribution shift, you get this, what they call the stability gap. Like as soon as the distribution changes, it causes the model to just catastrophically forget. And then your mitigation kind of recovers this. They show this for rehearsal-based methods, regularization-based methods, distillation-based methods, a lot of different methods to mitigate, trying to mitigate that setting. So I thought this looks like it slows down brain, right? Because you're going to go down and up, down and up. If we could just go, learn the new thing and not go plummet, we probably would need to update a few times. We had two hypotheses for why this occurred. One was excessive network plasticity. Two, we had large losses due to domain shift. And we developed some methods to test these hypotheses, and these led us to develop our stability gap mitigation method, which we can plug into pretty much an arbitrary skill learning algorithm. So our first hypothesis was due to having a large loss at the output layer. And the way people train these things is with what's known as hard targets. So you basically have a one-hop vector, a one in the correct category. And so if you had a domain shift involving categorization, right, in this class incremental space, you're going to end up, the system's going to get a massive loss, meaning it's going to say you're very, very, very wrong, make a big update. And as soon as it sees this in class, and that's going to cause a plummet. So we thought, okay, well, how can we address that? Well, what we can do is initialize the output layer weights to the mean of the new data for doing something like classical learning. So just, rather than randomly initialize it to the embeddings of the data as it's seen and just format. Two, we then thought, okay, even that may not be enough. We also have this whole, hard target, soft target thing I was mentioning earlier. And instead, what we can do is, why do we need to use the one-hop vector? Why don't we instead use a soft target where the thing we want is higher than others, but the other things are told to be zero, which then tells it, they have a very strong loss. This is used to play with that, but ours is not a uniform. So, and in this plot, you can kind of see that both of these things, so this is one-hop vectors, do nothing. This is our soft targets. This is the weight initialization. They all reduce the loss a lot on the output layer. So that was just to show you, not show you they overcome the stability gap, but they make the loss a little lower. The second one was the plasticity one. So we had two of these. One, a method that's very popular in NLP called low rank adaptation, or LoRa, which basically keeps a chunk of the network frozen, but then you have these adaptation parameters that are initialized to zero, which are then learned where only what the rank of these two matrices is, well, the product of these matrices is very low because they're both kind of have not very many parameters. But you both blend together and they form a matrix of the appropriate size. So then you have your pre-trained weights, then you add in this adapter and just learn these adapters parameters. So this gives you a way to control plasticity. It's extremely used in NLP right now and to update large language models and things like diffusion. So that's that idea. And what we see is that if we incorporate those methods, well, performance is no longer plummeting, right? It's like no longer doing this after we kind of controlling plasticity better. We also did whole output class review. This is my student's idea. This is only applicable to class incremental learning, but you learn a new thing, and basically to generalize it, if you just freeze everything, but basically when you're doing class incremental learning, you're only allowed to update the output unit of the new class. Otherwise, basically, everything in your output layer is frozen. The only you can update is the latent representation. Okay, so that's that idea. When we do this, we're still adopting kind of like our wake sleep framework still. So the lower weights are folded in. So basically during the sleep phase, BNA or learn, W is fixed. After BNA or learn, it wakes up. We can just add it in and then reinitialize it. So that's that idea. Explain those. And after we do that, we find that our method, as you kind of increase the number of classes here, stays very high in terms of performance, and doesn't decrease in performance as much, and has good accuracy on all the tasks. You see the accuracy on the old tasks here, it's not decreasing nearly as much. Specific example. But here's our main results. So in the compute budget, here's using a conventional method with rehearsal, with basically unlimited memory. It never even catches up to the offline model. But ours actually ends up, reaching better performance than the offline model, and it's kind of not that many updates, and provides a 16x beta. I feel like this plot is missing some units here, but I'll have to check with my student about that. I just noticed that. But yeah, so, and we combined it with a bunch of other people's methods. So we combined it with DERP and GDOM, the digital learning method, to show that it improves performance. We show that it works for various buffer sizes, and we found it increased our remind algorithm performance. One of our reviewers said, does it work for online learning? So we have the algorithm for you. So it works there too. And 7% gain or so, absolute. And it even worked on a regularization method, a non-rehearsal method, which is learning without forgetting. And it's it fails in classical fundamental learning normally. And you can see it did. But with this method, it's only it'll work not that great, but work much, much, much better than before. So you might have asked, why did this work even better than the offline model? That's kind of surprising. And notice here we're just measuring performance on old tasks. So here we're just measuring performance on basically the models initialized with ImageNet, and we learn the places data set, which has about 600 categories of scenes, right? It's very different. So we're just measuring the stability gap on the old data set. That's where you see it happen, the old performance. Why did this happen? Why are we performing better? So it's something about what we're doing, and we don't fully understand this, seems to be facilitating positive transfer from the new task to the old task. That's really the only plausible explanation for why performance was built up. So ImageNet performance went up. Efficiency, yeah, it also became a more efficient learner over time. I think we did more analysis here, but you can kind of see we have, so here's recovery of the offline model's performance, and then here's with our mechanism, and here's without our mechanism. So without our mechanism, you can see basically it never recovered. With this, so this is batch, like batch 1, batch 2, batch 3, batch 4, batch 5. So here, it took 60 updates, then it took 450 updates to recover, 98% of it offline model performance. And then never, right? With our method, we're able to recover, the performance of the offline model. It seems like we're not really sure if they're decreasing numbers, but it looks like they might be decreasing. And our hope was we're becoming a more efficient learner over time. So yeah, that's what I really am aiming for, is a more efficient learner over time. Because then, hopefully we'll be able to achieve things like low shot learning. So more work needs to be done in that. Okay, field learning beyond classification. So there are fundamental problems with field learning are kind of universal to deep learning, but the algorithms we just discussed are specific to supervised learning and particular classification. It's hard to construct regression problems where they're appropriate. But it's essential reinforcement, because you can't do reinforcement learning in general without doing some method to overcome this problem. Where in reinforcement learning, we have to take actions, and that will give observation, and then get a reward, and existing reinforcement learning algorithms are even more inefficient than our supervised learners, right? So you can make systems that work great, beat superhuman. How AlphaGo was made, best Go playing, well, not the best Go playing algorithm now, I think, like AlphaZero, maybe, or the AlphaStar. But they were the first one to beat humans. They could use reinforcement, but it needs to learn a long time. So, like Dota 2's AI required the equivalent of 45,000 years of human experience to beat the world's best players. They trained it for 10,000 in a class. That's a lot of time in the simulator for it to get good. So, can we do better? I mean, humans played did better. We've only been out like a few years. So, with these two people right there, we're proposing to try to address this. So, we're got a little project here to build on Professor Lerner's theory to study this NSF on the NSF award to see if we can adapt skill learning to these kinds of problems and ideas under the temporal scaffolding hypothesis. So that's I'm very excited to work on this and recruit students to start working on it in spring. He's attending some meetings, warming up right now. But I'm really excited. And then we have a lot of it. I mean, if we were successful, it's going to be hard. If we were successful, that would have a ton of impact. If remember those carbon emissions? Like OpenAI Dactyl. This is a thing that it's a robot that learns in a simulator to solve Rubik's cubes. It drops the Rubik's cube 9 out of 10 times, and it uses the equivalent power to train it of 2 nuclear power plants for 1 hour. Like, so that's a lot of energy, right? Can we make things better? Anyways, I have to thank all my students and my sponsors. Most of this work I presented, was driven by Yusuf, Jair helped us some, and Ron helped a little bit on some of these projects. But so computer learning has a lot of real-world applications, I think, and I think we should design algorithms for those applications. They should be about scaling and efficiency. The 3 papers I presented on archive, and 1 has been accepted now. Hopefully the other 2 will too. Thank you. Yes.
Great talk, Chris. Thank you very much. 2 questions. One kind of a more general question on continual learning. Obviously, I don't work in this area, but I'm assuming a lot of the results are presented as data that is clean. What happens and how do you deal with maybe poison data?
Poison's an interesting question. But one mechanism, I mean, the main way you would, there's different learning kind of methods. Most performant ones are these ones like that are rehearsal based, which is why I was focusing on that, because they're the only ones we know that can match real world needs. In the rehearsal, you kind of have this buffer, and you can manage this buffer. And so issues like label noise or data set poisoning, you might be able to detect it through a sampling policy to detect things that are kind of erroneous. Like, for example, if you'd have to figure out a way to make it efficient, but if you had a point and you could see that its neighbors were all of a different class, right? Maybe that sample should not be sampled. But, you can then use intelligent sampling. Like what I'm kind of focusing on now is intelligent sampling. So you could build that into your sampling policy to maybe try to catch that problem. I don't know if anybody studied this. There's been a couple papers doing this with label noise, but I don't know if anybody studied it. It's an interesting idea. Like in the wild, I think if you were to deploy something like this in the wild, just hoover data up, probably something cognizant of.
A more kind of specific question on your grasp sampling technique. What are the intuition of why we sample that way?
So it was inspired by this paper. They developed a theory using statistical mechanics, which I didn't fully, I could understand all their results. The theory I kind of glossed over, to be honest. But why that happens, it's not 100% clear, but that makes it inspiring to say, well, we're trying to come up with all these policies that like, this is the right thing to do, but what it may be the right thing needs to do changes over time. And so just to have an adaptive policy. And we're just saying this is just a starting point, at the very least, I think our work, because I mean, I chat with so many people out there who try to find something and fail, and nobody publishes null results. So I think it's an exciting area for people to research. And I hope that this kind of reawakens people to it being valuable. I'm sure you can do better than this. Somebody could do better than this. Maybe I don't know. Yeah, Inamar.
Yeah, so one very, very general question, one just specific one, a specific graph. The general question is, am I right to, did I understand it right that all the algorithms that you presented, they're not only on supervised learning, but they're also all stationary, like the examples are stationary, they're not like it's a picture, not a movie.
Oh, yeah. So I've done work on that movie problem. All these were stationary. Correct.
Right. Okay. And then in particular on the graph where you showed I think it was the glass model where you showed us like an advantage. Go back.
Yeah, graph. Okay, going back.
One more, I guess. Yeah, this exactly. So it's very, very small differences in terms of accuracy, and it almost looks like also the graph is ending early. What if you let it?
Yeah, you let it keep training. It's a good question
Because it only reaches 60-something%. Everything else.
Yeah, it's a good question.
It's like at 60% that you gain almost nothing, and then at 63,
yeah,
you get a lot.
It's a very good question, Omar. Why did we not keep training? I don't have an answer, unfortunately.
Maybe it closes.
Yeah, I'm sure it was. Well, we're up against the deadline. And we're like, okay, it's good. So we made our point.
Yeah.
Right. We made our point. So stop then. But yeah, there's no reason we couldn't have said it longer.
As long as you're sure that it's going to grow and grow, right? Because
it's interesting with plateaus too, though, right? Like I wouldn't think it would necessarily. I think that would be still interesting, but it'd be nice if it kept growing. But when does it plateau? It hasn't plateaued.
But could it close?
Yeah, I don't know what would happen. It's a good question. I should ask.
62 it seems like why there? Why 62? Why?
Oh, it's going to plateau. Like all of these things hit an upper bound just due to the nature of the current problem. The current state of the art, if you throw everything you got at ImageNet, and even, if you train on the largest data set in the world that Google did recently for supervised learning, and then self-supervised learning, I think, and then they fine-tuned it on ImageNet, they only hit 90%. So that's like the best result. So there's still, you can't get perfect.
No, 90 is fine.
Yeah.
90 is more than 60, right? So
90 better than 60.
Yeah.
Right. But this is a very tiny, this is not scratch. This one, I think we're training on MobileNet network. So it's still, it hits upper bound pretty early because it's got limited capacity. The other one, this one actually, we're training something known as CombNext V2. So it's kind of like a bigger neural network. Yeah.
Maybe not. Yes, on the thin state, how is the power number compared to the weak state?
Sorry, what's the number you're asking about?
The power number, thin state.
Oh, the power consumption. Oh, I have, it's tricky. It should be a lot less because it just depends on how you're measuring this, right? But if you just ask the same budget, right? Because if you take the same number of samples, right, and you're looking at both, and during the wake stage, you're only doing a forward pass, whereas in the sleep stage, you're doing a backward pass. And the backward pass, so that requires about 3x more compute than the forward pass. So, right, if you do one forward pass, if you say how much did it cost to do it forward and backwards, about 3x. Okay.
Is there a question, please?
Yeah, so these, things here,
This is not using very intelligent replay, but this sampling from a uniform grasp is using the intelligent replay. Like
So-
sampling, let's say, if you're actually about the sampling policy.
Right. So when you as you increase the number of classes that you're, do you notice? I know you're saving a lot of your updates, but do you notice if the size of that update is increasing, or is that update size narrowing?
We're keeping it fixed, right? You have a fixed budget, and it's done. The sampling's done independently per
So
category.
maintaining a fixed budget, not increasing.
No, we're not increasing our budget. We keep the budget fixed always.
Okay.
Like, we don't want to have increasing budgets. You don't want to be. It takes you more time to learn as you learn. You don't want learning
That's
more
really
expensive over time.
Yeah, that's really interesting because as you increase costs, you would expect more samples to be played. But you're saying you keep
No, everything is kept the same. There's a fixed budget.
And what happens when they encounter like a lot of images share a lot of the distribution space. There's a lot of shared images.
Right.
What happens when there's a large distribution, like high deviation?
That would be so, like, for example, the stability gap one, we're studying, I should have put pictures in, but this is ImageNet to a sequence of place data set, like chunks of different scenes, like this is a forest, this is, I don't know, a meadow, this is whatever, an exciting San Antonio, I don't know, like whatever. So that one you have a big distribution shift. You're talking about it. Your distribution shift would be more like you're thinking the same categories but different times of day, like that.
Yeah, no, I was not like that would be domain, like a domain.
Yeah,
but I'm talking more about how that affects. If that was the difference in the classes themselves, that big a difference, how would that affect best shared information in these classes? So
yeah, it's a good question. There aren't really, I don't know if data. You don't have a good data set to test this. Yeah, I mean, sometimes we're locked out in by the
You're
data
right
sets
about
we
that.
have. Like one of the things I really want to work on is, what I tried working on in the past is learning from video data, right? Rather than learning from contiguous images. We did that for a few years, but the data set was too easy and too small, right? It wasn't that it was easy. It's not that the temporal sequences made it easier, it's just the data set was easy. It wasn't that long. It's like some person, here's this toy dog. Of course it is. Okay, next thing, okay? Here's a can. That was what the videos were like. So, we studied that and studied it with different distributions. But there's nothing, we're like bottlenecked by, we need better evaluation. I mean, I'm not satisfied at all with this doing ImageNet. But I'm very unsatisfied with superintendent.
I mean, it's a big jump
And
from
this.
sci-fi.
Yeah.
Thank you so much.
Yeah, I have a couple questions. I should have noted the slide numbers, but so you had that chart saying or kind of deck saying that the learning method.
No, my little chart.
Yeah, the chart in during the efficiency.
Yeah.
This so it's like a graph.
Oh,
I think it's a couple.
yeah, okay.
Oh, yeah, that one.
Yes.
Isn't this essentially invalidated if like the pre-trained model adaptation you shot with paradigm? Because say you train on 13.
Oh, so that's not, we were talking about a different paradigm, sort of. Like, what if we took like that model I mentioned earlier, like the one that just came out, gigantic model trained on, who knows how many billions of images, and then we now don't need to update it very much. Is that your kind of question?
Well, the continual learning part of it, so small compared to pre-trained. Data. So,
You're right.
So it would describe to be a lot probably even in the extreme case.
Yeah, the continual learning. I was at a continual learning kind of leadership retreat in March. Rachel was there, and this type of issue came up. So what is the role of continual learning in the era of foundation models? And I still think it can play a role, because I still think we need to update these models and personalize them. No, already people are doing this, like with adapters, like Laura. They'll want to customize them and use some things, update them a little bit. So, but then even then, what they'll do is create different banks of these things versus kind of like just continually, for each task versus just kind of integrating them over time. But yeah, it's something we're kind of wrangling with right now into this.
Okay, it also leads me to my next question, which is, so if I understood it correctly, when y'all use Laura to continue, y'all didn't see any, like, y'all saw backwards transfer.
Right, it looks like it. Yeah, I was pleasantly surprised. Panos, you had a question?
I had a quick question, but maybe we can leave it for later.
Okay.
So there are a few more questions. Let's wrap the discussion and it's a free flow. You can just reach out to Chris and talk to him for a few. So let's give a big round of applause for Thank you all for joining us today. To all the online participants, I think at some point the recording